When we do a lot of exploratory data analysis, sometimes we see some anomalies, some really weird results. And one such phenomena is called Simpson's paradox. In Simpson's paradox, we see different trends as we sort of split up this data. And when you do exploratory data analysis, you will do a lot of splitting up data. But the more you do that, the more likely you are to come across Simpson's paradox. That's why I think it's important to talk about. So in this video, we're going to show some examples of Simpson's paradox, and then we're going to diagnose what's causing that weird phenomenon. So what is Simpson's paradox? It's a phenomenon where splitting the data can result in opposite trends. So if we split it in one way, we get certain trends, and if we either don't split it or split it in a different way, we get the opposite trend. A famous example of this is treatment for kidney stones. So there was a study on two different treatments, treatment A and treatment B, and they were treating two different types of kidney stones, small stones and large stones. This table shows how successful the treatments were. So for treatment A on small stones, 81 out of 87 patients were cured. Treatment B on small stones, 234 out of 270 patients were cured, and so on. And we want to know what treatment performs best. So for small stones, treatment A performed best, 93% cure rate is better than 87% cure rate. And for large stones, treatment A also performed best, 73% cure rate is better than 69% cure rate. But when you aggregate the data so that you don't care about the size of the stones, then overall 273 out of 350 patients were cured by treatment A, but 289 out of 350 patients were cured by treatment B. So treatment B performed better overall, but for each subcategory, treatment A performed better. And this was really weird. So when you see this case, you then got to ask, was splitting by small and large stones a sensible thing to do? And you've got to go back to the experts to ask that. Another example, and this was in Florida in 1976 to 1977, looking at whether there was any discrimination in the justice system on a racial basis. So were black people getting death sentences more often than white people? So when they looked at the data, they split the data up into whether the defendant was white or black and whether the victim was white or black. And when there was a white defendant and a white victim, 13% of defendants were put to death. When there was a white victim and a black defendant, 17% of defendants, and so on. So now if we look at each race of victim, so when there were white victims, the black defendants were more likely to be put to death, and when there were black victims, the black defendants were more likely to be put to death. So this was some form of evidence of that there's racial discrimination going on here. But when they aggregated the data, so you didn't care about the race of the victim, well, actually 12% of white defendants were put to death, but only 10% of black defendants were put to death. So what's going on here? Well, actually, in this case, we were interested in the wrong split. We were looking at whether there were racial discrimination amongst the defendants. What we should have been looking at was there racial discrimination with the victims. 14% of all defendants were put to death when the victim was white, and 5% of all defendants were put to death when the victim was black. So actually what this phenomena showed was that they split, even though they were splitting on the right things, they were focusing on the wrong things. Simpson's paradox can happen with racial interval data as well. So when we have scatter plots, for example, this example actually comes from this brilliant YouTube video which explains Simpson's paradox a lot better than I can. So I really recommend you watch that video. And in this example, you can see here we have two scatter plots of how happy you are versus how much money you have, whether you're a cat or whether you're a human. And we can see both these categories have a negative relationship. Right? The more money you have, the less happy you are, whether you're a cat or you're a human. Okay, clear cut. But when we aggregate, so we don't care what species you are, we get this. And now it looks like There's a positive trend. The best fit line is actually a positive trend. The more money you have, the happier you are. Even though individually each category had a negative trend. So as we split by category, we get opposite trends to the aggregated data. And this example really shows how silly this is. This shows that the more money you have, you turn into a cat. But when we have silly examples like this and we know the context of the data, it seems silly. But when we don't know the context of the data, and the only context we know is what we are plotting, it becomes really, really difficult to recognize these things. And this actually happened when analysing data on the coronavirus. So right at the start of the pandemic, when the epicenters of the pandemic were China and Italy, researchers looked at whether China or Italy were doing better with death rate. So they split up the population into age bands, so 0 to 9, 10 to 19, 20 to 29 and so on. And they looked at the death rate within those age bands for China and the death rate within those age bands for Italy. And for every age band, China had a higher death rate than Italy. But overall, when you didn't care about age, overall, this last column here, Italy had a much higher death rate than China. What's going on there? That's really weird. Well, what's actually happening and what this graph shows and what we know now is that coronavirus hits elderly people worse than younger people. And when we look at the demographics of the two countries, Italy has a lot more older people than China. So Simpson's paradox is occurring here because we have different sizes of groups and we are comparing different sizes of groups. So some of the reasons that we've sort of diagnosed in this video for why Simpson's paradox can happen. There's extreme size differences in the groups that you're splitting on, and that's what happened in the coronavirus example. You were splitting by an irrelevant factor, and that's what happened in the racial discrimination example. You were splitting by defendant when we should have been splitting by victim. Or you've split fundamentally different groups which are incomparable. For example, the cat's money happiness example.